I need to run here from bioscience.
So I have the great pleasure of introducing one of my very first research students here at Lawrence, Julia Jaglowski. I kind of said it right. I always get it wrong. Everybody always gets it wrong. But it's been a really great pleasure to have her in my lab. I met her in my very first class I taught at Lawrence when I had no idea what I was doing. And she was in the chem lab for the first time, and I think she had no idea what we were doing. And we kind of followed that theme along and struggled through putting together my lab, building Artemis, which she'll tell you all about, and then figuring out what the heck to do with this data we collected as we went through Artemis. It does mean I've seen Julia in wonderful and unique circumstances. She is a very competitive cow player. She really likes to slaughter people's cows, so be a little careful around her. She also has helped me find a very creepy restaurant in the middle of North Dakota that we sit outside going, should we go in? Should we not go in? Should we go in? And we ended up having a lovely beer together there. But I cannot say how proud I am to have her presenting today. She has provided me with inspiration as I've started to build myself here at Lawrence. It's been a privilege to have her as a student, and I welcome her with great pleasure to the stage to talk about her research. By the way, she's from Chicago, I forgot.
I'm pretty sure most people there. Hi, so like Deanna said, my name is Julia Jaglowski, and my presentation is titled Regional Air Quality Study of the Williston Basin using Artemis as a novel mobile laboratory. And just a quick overview, I will be talking about the atmosphere, what the atmosphere is made of, how small concentrations in the atmosphere could have large impacts. Then I'll go into photochemical smog, which is the focus of my study, how photochemical smog is produced, and then the methodology we used in order to collect data, the results of our data, and then lastly the conclusions of said results. Oh my god! Okay, so the atmosphere is it's very large, more than 500 kilometers in height. But really when we're thinking about the atmosphere and when you hear the word atmosphere, you're probably thinking about where we're living, which is the troposphere. And that goes from the surface of the Earth up until about 11 kilometers. So what is the atmosphere made up of? Primarily oxygen and nitrogen, and small concentrations of argon and carbon dioxide. And then there's this other category, other gases. And these other gases are comprised of a variety of different gases in very small concentrations. So an example of these small concentrations that make up that category is ozone. So ozone is in the atmosphere is about 0.000007% in parts per million. So to give more context that's even more relatable in terms of parts per million, 1 part per million is equivalent to 1 minute in 2 years. A part per billion is 1 kernel of corn in a 45-foot tall and 16-foot wide grain silo. A part per trillion is 1 drop of detergent in dishwater that would fill a row of train cars 10 miles long. So these are tiny concentrations. And I wanted to give a few examples of how these small concentrations could have large impacts in terms of air quality. So my first example is going to be lead. And lead's specifically from leaded gasoline. So throughout the industrial era, leaded gasoline became a very important energy source for us. And it was emitted through vehicles and industrial activities. And up until about the 1980s, there was no regulations for lead emissions. And that's primarily because we had been emitting lead into the atmosphere for centuries. It's not something new. So a few studies were done in the early 1980s that suggested that, that had found real proof saying that lead had adverse effects both on air quality as well as human health and plants and animals alike. So the EPA put a standard of lead at 1.5 micrograms per cubic meter. So you can see here when these regulations started coming into play, and the x-axis here is from just showing the years from 1980 until 2014, and these are the lead concentrations in micrograms per cubic meter. So when the regulations came into play, the average concentrations of lead in the air were about 1.5 microgram per cubic meter. And the maximums of lead in the air were about a little bit more than 2.5 micrograms per cubic meter. So you can see this trend here that once the regulation came into play, the concentrations of lead from leaded gasoline decreased significantly to a point where we have very little lead in, or it's either under the EPA standard or right about at the EPA standard of 1.5 micrograms per cubic meter. So you can consider this a success story in terms of reduction. Another example is going to be acid rain. So acid rain occurs when CO2 is emitted from industrial, or SO2, not CO2, SO2 is emitted from industrial activities. And SO2, once it gets into the atmosphere, reacts with water and oxygen to create sulfuric acid. And this sulfuric acid accumulates in clouds and then is deposited back to the Earth's surface through rain. And you can see in this picture here that these trees, this degradation on these trees in plant life is occurring due to this acid rain. Fortunately though, in the past several years, SO2 regulations have become stricter, so they've reduced, the concentrations of SO2 emissions have decreased, and therefore sulfuric acid concentrations in the air also decreased. So we're seeing much less acid rain. And now I'm going to go into photochemical smog. And photochemical smog is going to be the focus of my study, and photochemical smog occurs when there are high concentrations of nitrogen oxides and volatile organic compounds, and in the presence of sunlight this produces tropospheric ozone. You can see in the figure here, this is Los Angeles during a smog event, or a photochemical smog event, and here this is the accumulation of nitrogen oxides, volatile organic compounds, and tropospheric ozone, which sort of gives it this brown tinge. And then in this photo here, excuse me, in this photo here, this is Los Angeles without, or in a not photochemical smog event. So this is sort of suggesting this idea that certain conditions need to be met in order for photochemical smog to be present. So now that I've introduced photochemical smog, I wanted to go in more detail about the components of photochemical smog. So nitrogen oxides. These are highly reactive gases that cycle between NO and NO2 very rapidly. And here you can see this is a very simple diagram of this cycling. So when NO2 is present in the air, it is photolysed by sunlight, meaning sunlight provides energy in order to break the nitrogen-oxygen bond to produce NO. And then in the presence of O2, which is abundant in the atmosphere, NO will react with O2 to produce NO2 again. And so you can see that in the presence of both sunlight and oxygen, this cycling is going to occur rapidly. So atmospheric chemists account for both NO2 and NO concentrations with this term called NOx, or NOx, because you want to account for both concentrations in order to understand the overall concentrations. So there are several sources of NO2, primarily fossil fuel combustion, such as or from vehicle traffic as well as industrial activities. And there are negative health effects associated with overexposure. So that can include eye irritation, respiratory irritation, and with extensive exposure, respiratory diseases. Another component of photochemical smog are volatile organic compounds. And volatile organic compounds are organic compounds that are readily vapors and gases at room temperature. And these are produced primarily from burning fossil fuels, as well as being emitted from oil and gas fields that are trying to extract these oils and natural gases from the earth. And volatile organic compounds can also cause adverse health effects, primarily headaches, memory loss, eye irritation, as well as respiratory irritation. And lastly, tropospheric ozone. So I'm sure most of you thought, once I mentioned ozone, that I was talking about the ozone layer, or good ozone. So the ozone layer is in the stratosphere, and that's higher up from the troposphere. And we do want high concentrations of ozone here to protect us from sunlight and radiation. But the bad ozone that I'm going to be focusing on is in the troposphere, so where we're living, where we're breathing, and the ozone that we're creating through anthropogenic sources. So in high concentrations of nitrogen oxides and volatile organic compounds, this will encourage the production of ozone. And in the abundance of tropospheric ozone, nitrogen oxides, and volatile organic compounds, this can lead to photochemical smog. And there are adverse health effects associated with this as well, primarily eye irritation and respiratory irritation, as well as respiratory diseases with long-term exposure. So now that I've introduced all the components of photochemical smog, I want to go more into detail about how tropospheric ozone is produced. So this is the overall cycle of producing tropospheric ozone, and I'm going to go through it step by step. So in order to make ozone, we need to put in an ozone. So this ozone will be photolysed by sunlight, or the sunlight will provide, meaning the sunlight will provide energy in order to break the oxygen-oxygen bond to produce this hydroxyl. And this hydroxyl is essentially the detergent of the atmosphere. It reacts with almost anything to make it more water soluble in order for it to be deposited back to the Earth's surface. So, in the presence of volatile organic compounds, it said hydroxyl will react with it to produce this RO2. And this RO2 is just a more reactive version of the volatile organic compound that was originally present, which will then react with an NO to produce an NO2. This NO2 will then again be photolysed by sunlight to produce ozone. And then we're left with this RO here, which will react with oxygen in the air to produce an oxidation product. Depending on what the composition of the volatile organic compound that was originally entered into the cycle, this oxidation product could come back onto this side to restart the cycle of the production of ozone. And it also produces this HO2. And the HO2 reacts very similarly to the RO2. So it reacts with an NO2 or an NO to produce an NO2, and in the presence of sunlight will create ozone. However, it is extremely important to note that this is not the end of the cycle. This can continue occurring over and over and over and over again. So one of the important things to note that I mentioned earlier, this oxidation product can come back and restart this cycle over and over again. And in some cases, one volatile organic compound can be responsible for up to production of 50 ozones, just as an example. So now that I've introduced this, so now that I've described the production of tropospheric ozone, I want to go into places that may be susceptible to photochemical smog production. This figure here is a picture of the United States. I'm hoping you all knew that. You can see in this light pink here, this is showing basins, and basins are places where there are high reserves of natural gases and oils. And then the dark pink here is where they're extracting these natural gases and oils from the earth. So why is this relevant? What are they doing there? Well, the primary extraction method is hydraulic fracturing. And hydraulic fracturing is the process of drilling a well deep below the Earth's surface into this dark rock here called shale rock, where natural gases and oils are stored. And what they do once the well is created is they create these small explosions in order to break the rock to release these natural gases and oils. And then they introduce this fluid called fracturing fluid, which helps with the extraction of these natural gases and oils that will then come back up to the Earth's surface and be stored on site until removal. And after the extraction of these oils and natural gases, it's they generally want to recycle this fracturing fluid. So they'll store it on these water recovery tanks on site to be reused. And this is relevant because it's possible that volatile organic compounds or remnants of them are being left in this fracturing fluid. So the reason that these locations are so susceptible to tropospheric ozone production and then in that case the photochemical smog production is because volatile organic compounds can be evaporate from these fracturing fracturing fluid collection tanks. And considering the fact that I told you before that volatile organic compounds evaporate at room temperature, this may be contributing to the volatile organic compound concentrations in the air. And another process that's very common in hydraulic fracturing is this process of flaring. You can see in this picture here, this is a flare that we saw on the field campaign that we performed over the summer of last year. And that's the process of burning off volatile organic compounds that escape from fracking wells. And the reason that they do this is primarily to reduce the amount of volatile organic compounds that are being released into the atmosphere, but it might not be accounting for all of the volatile organic compounds that are escaping from these wells. So that can also contribute to the concentrations of VOCs in the air. And another component, or another contributing factor to these concentrations can be increased vehicle traffic and industrial activities, which can contribute to the nitrogen oxide and volatile organic compound concentrations in the air as well. So then I've talked about why these places are relevant. I'm going to look more in detail at one of the place that we thought was most important in terms of where we wanted to study, which is the Williston Basin Bakken Formation. So it's approximately 150 square miles and is rich in oils and natural gases. And that's the places that the hydraulic fracturing is occurring most primarily is in these colored regions here. And because of the immense amount of hydraulic fracturing, North Dakota has become the #2 oil producer in the US in just a short amount of time. So prior to getting into our methodology and our data collection, I wanted to show a video that demonstrates another research group's data collection, or a simulation of what they saw based on their data. So, what they're showing here is the changes in ozone concentration. So what they did during their research is they collected data on halogen or hydrocarbon concentrations, specifically ethane. And you can see here this movement, and what they're showing here is the ozone concentration. So higher changes in ozone concentrations are going to be in the dark colors, and lower changes in ozone concentration are in the light. So you can see this movement of the air. From this simulation, they're suggesting that the source is the Bakken Formation, where all this hydraulic fracturing is occurring, as well as how this may be affecting other places in the United States as well as outside of the United States based on this wind movement that's occurring, or this normal cycling of the wind. So what they did is they compared, or they made two simulations. They looked at a simulation based on their ethane concentration measurements, and then they did a simulation based on the concentrations that they were expecting to see prior to this hydraulic fracturing. And then they determined the ozone difference. So based on that simulation, they were able to see that the hydraulic fracturing that's occurring primarily in North Dakota is having large impacts on changes in ozone concentrations. So now I wanted to look more, So now I wanted to go into our methodology and data collection. So this map here is a map of our field campaign, the path that we drove on when we were collecting our data, which is in blue here. And the field campaign lasted from August 15th until August 28th, and we collected data from August 16th until August 27th. And it covered 3,235 miles through North Dakota, South Dakota, and Montana. So, and one of the primary reasons we wanted to go out here is because we did expect to see some very interesting atmospheric chemistry, considering the amount of hydraulic fracturing that's occurring, as well as the fact that it's sort of in our back door. It's easy to drive to, so it seemed convenient for us to go out there. So how are we measuring things? Well, we stopped at 49 different sites, and we measured a variety of different things for about an hour each. And we generally just stopped on the side of the road and collected data for that hour. And it's important to note that we did calibrate our instruments both morning and evening. So what were we measuring there? Well, first off, this right here is Artemis. It stands for Atmospheric Research Trailer for Environmental Measurements and Interactive Science. So Artemis essentially held all of our instruments as well as tools we needed in order to make this campaign successful. And another important thing that I just want to point out here, this pole is a PVC pipe pole that we made that's anchored by Artemis's wheel right on the other side. It's not a light pole, considering, you know, there's wires in the background. So the first instrument I'm going to talk about is the Kestrel 4500, which is a mobile weather station. And it measures a variety of different things. But the things that we focused on most importantly were relative humidity, temperature, wind speed, and wind direction. Another instrument that we had was the optical particle sizer. So what this does is it collects particles and sorts them into their size. So there's two standard sizes in terms of particles, and that's 2.5 and PM 2.5 and PM 10. And then upon collecting these and sorting them into their designated sizes, it also is able to tell you the total counts of specific sizes as well as the overall particle counts. Another instrument we had was our ozone monitor, which makes sense. We were trying to see whether or not there was higher concentrations of the tropospheric ozone. Then we had our nitrogen oxide monitor. We had a stellar net spectrometer, which is essentially measuring the intensity of light. And then we had Little Apollo, which is a project created by Mikhail Trout, an instrument that, and she's presenting right after me, so if you're interested, you should go see that. But it measures CO2, relative humidity, temperature, and particles. So we got all this data, we had all this instrumentation. Where do we go from here? So I wanted to show this sort of complicated figure. On the x-axis here, this is showing all of our sites as well as all the days that we measured. And in red, or not in red, but in each specific color designates as one day. And then on the x-axis, or on the y-axis, we were looking at ozone concentrations. So this is all of our data at 1 minute averages, so that's about 3,000 points of ozone. So a few things I wanted you to take from this figure is the fact that there are some obvious trends that we can see here. And to give a little bit more context, these are box and whisker plots. So in the line in the middle of the box, generally in the middle of the boxes is showing the median. Then we have the maximum at the top of this line, the minimum at the bottom of this line, and then the 75th and then 25th percentile. So one of the trends I wanted you to notice is the fact that as it got later in the day, ozone concentrations tended to increase, which is something that makes sense to us because we expect as it gets later in the day that temperatures are going to increase. So that's going to influence ozone concentrations, and I'll get more in detail on that in just a moment. But another thing I wanted you to take away from this is that this region here is what we thought was going to be what we saw as the fracking region. And this has the highest ozone concentrations in general, as well as the most variation in ozone concentrations. So great, we have all this data, but what are we going to do with it? So there's a few questions we have. How do we decide what is background data? So we want to look at concentrations of ozone that we expect to see that isn't influenced by fracking activity. What data do we want to look at first? I mean, I told you how many instruments we had, so clearly there's a lot of data that we can look at to see whether or not there's any relationships or anything that's interesting. What is ozone dependent on? If ozone is dependent on some variable, how do we remove this dependency so we can look strictly at the ozone, the changes in ozone concentrations? So like I said just moments ago, ozone is dependent on temperature. So as temperatures increased, we also saw that ozone concentrations tended to increase. And this is a very simple concept in chemistry or in any sort of reaction. The fact that you add energy to a reaction is going to increase the rate of the reaction, and therefore increase the concentration of the product that you're looking for. So ozone is also dependent on relative humidity. And as relative humidity increased, ozone concentrations tended to increase, or decrease, excuse me. And the reason for this occurring is because as the moisture in the air increased, it would scavenge out ozone particles, for instance, ozone concentrations, or ozone components in the atmosphere, for instance, and deposit that back to the Earth's surface through rain. So it makes sense that we would see this trend. So now that I've showed you the trends that we expected to see, I wanted to go more in detail about how we're going to decide background versus fracking regions. So this figure here is very similar to the figure I showed you before of the map that we went on, except this is looking at average ozone concentrations per site. So in black, I'm showing, this is the background regions, or the sites that we decided were going to be background regions. And then in red is the fracking region here. So one of the reasons that we consider these background regions, because you remember that video that I showed you and how the wind seems to move upward? This upward movement is going to be considered upwind data, and this is going to be downwind data, specifically from the fracking region. And then this area here could also be considered downwind data, depending on the direction of the wind for that in a particular day. So we wanted to make sure that we got data on all sides of the fracking region so we can see whether or not ozone concentrations vary depending on the region. So great, now we know our background data. We took this background data and we did a polynomial fit, or a second order polynomial fit, and this is strictly a background data versus relative humidity and temperature. And we wanted to make relative humidity over temperature one variable, so that we didn't have to deal with two separate variables. So it's just easier to make it into a ratio. And then ozone concentrations on the y-axis. From this fit, we were able to solve for expected ozone concentrations based on the background data. And then we took these expected concentrations and subtracted them from our observed ozone concentrations in order to get ozone difference. And we were able to then make this figure here of our ozone difference on the y and the relative humidity over temperature on the x. And you can see here by the dark line, this is the average concentrations of ozone, or ozone difference, and then the standard deviation in the plus and minus. So you can see that what we did, we were trying to make it so that our background data was at 0, or roughly at 0, which is what we did, and it ended up working out well. Now we wanted to compare that to our fracking region data, which is in the red. You can see this is the average and then the positive and minus standard deviation. And you can see that the average ozone concentrations in fracking regions in terms of ozone difference are 8.06 parts per billion. This is huge. And we did a t-test of unequal variance to see whether or not this was statistically significant, and it was. So this is really, really important information. We are able to see that fracking regions have an influence on ozone concentrations. So just to make sure we weren't getting ahead of ourselves, we wanted to do one more test. So this is all of our data, so all 3,000 points averaged at 1 minute, ozone concentrations versus time. You can see here that there are some trends that we see in variations in the ozone concentrations depending on the time of day. So we wanted to take our ozone difference and see whether or not that changed, that made it so that this variation and these trends were not seen, to make sure that we weren't crazy, that our zeroing method was working. And we did see that. You can see that this data here is very clumped together now. There's less trends overall. However, I did just want to point out here that this section is data that we collected on a day where we were getting information or data from a fire that we were, the smoke from a fire that was coming from Washington, Oregon. So that's great. Our zeroing method worked. We saw that there was differences between the fracking and the background regions. So I just want to do an overall conclusion. So Artemis worked really well. It was able to withstand gravel roads, as well as lug all of our instruments and tools around throughout these 14 days. And that's awesome. We're really grateful that it worked out really well. We also collected an outstanding amount of data. There's data that we haven't even looked at yet, that we just had, there's no time. The amount of data we have is immense. And again, I really want you guys to take this home. The fracking region ozone concentrations compared to the background regions were 8.6 parts per billion greater. So remember how I told you at the beginning that small concentrations have a big impact? Well, this is having a big impact. Future work. I just wanted to go into a little detail about things that we might be doing in the future. So studies in terms of fracking. Well, we want to look at ozone differences in the relationship it has with CO2 concentrations. Also be interesting to go to the Marcellus Shale, which is another region that has high fracking activity, and that's mainly located throughout Pennsylvania, in collaboration with Katie Farnsworth at Indiana University, Pennsylvania. And then studies including Artemis. Well, right now we're in the process of creating a max DOIS, which will measure halogen concentrations. And it'd be interesting to go to the Great Salt Lake to study ozone, halogen, and mercury chemistry because of the great variations due to the influences depending on the environment. And we'd also, it'd be interesting to study at Adams Farm, which is a farm that has an affiliation with Lawrence and isn't too far out from here. And the Environmental Studies Department works with them pretty closely. And we'd want to look at air quality around fracking sand mines as well as grain terminal activities. So that's the whole of my presentation. There's just a few acknowledgements I wanted to put out there. Again, I wanted to thank Deanna Donahue for everything that she's done for me over the past 2 years. She's taken me under her wing, given me the opportunity to study atmospheric chemistry, went on a successful field campaign, helped me slew through all of this data. I wanted to thank David Junes, who also participated in the field campaign and helped with the planning process and some of the data. I also wanted to thank Miko. I mean, she contributed Little Apollo to our field campaign, gave us some other interesting data, and Daniel Martin for everything that he's done, especially with the planning process and the prepping for the field campaign, which was crazy. And then Dave Hall for all of his contributions in terms of Chem 680 and all the positive feedback he's given me to create this presentation, and all of my friends, people from Chem 680 for all of their feedback, as well as my family, because I wouldn't have gotten here without them. So my references, any questions? Yes, Sam.
Wait, I'm assuming this data has been published now?
No.
No, not yet.
No.
And do you think if it does, like, I don't know anything about environmental work, but would the people in charge of the fracking, like, what would happen with that? Would they, like, pay for you to, like, try to cover it up or something?
I mean, I don't know anything I read the
like
publication
wondering
process.
how like that goes in like environmental stuff.
Well, I mean, I believe it would just be like a paper that's put out there, and then based on that information, other things can come into play after that, right?
Yeah, I would say this is not bigger than a city influence, and so I think the argument that would be made is this is just like a city. And so are we gonna take down all our cities? And that's the argument that you often hear. So I think it's more just to be aware, there is some debate of whether the ozone really happens. It's hard to catch. And that's why we're pulling over on the side of the road. And so even just confirming that it's there is a novel observation. We figured this out like a week and a half ago.
Yeah.
So it would just be information.
Yes, Emily.
This is just a simple question. Do you need permission to, were you on public land?
So what we did, I mean, in terms of pulling off on the side of the road is, I mean, if there was no sign saying we couldn't, we would. And I mean, we had our maps planned out for the most part of what roads we'd be taking. And for the majority of the time, we were on pretty small roads. So it's just easy to pull off to the side, set up, take sample for an hour, and then leave. Without a trace.
So you
Yes. Oh, sorry, no, go ahead, Emily.
No, I'm sorry, just so you
Yeah,
didn't
go
run
ahead.
into any like fracking.
I mean, there was a few times where a couple people just stopped and asked if we were okay, but it wasn't like, you know, get off of our land. Like, it was just more like, you know, is there anything wrong with your car, sort of thing.
Goodness is gracious.
Yes.
On one of your concluding slides where you try to come up with the expected ozone concentration, you chose to do a second degree polynomial fit. I'm just wondering if the data suggested that to you, or if there was a reason you.
I mean, it was really just an empirical fit. We wanted to see whether, like, we saw this trend, we were like, second order polynomial would probably be good. We fit it, it worked out. Yes, Dave.
Can you go to the one with the little circles where the ozone concentrations were? Yeah, right there. So there are two at the very bottom that aren't included in any of the circle. What was there any? There's lots of ozone there. Was there
The
anything
primary reason
unique?
we didn't include those is because the last day we were at truck stops or rest stops.
Okay.
So a lot of that information is really just like car traffic.
Okay, so those are attributable to car traffic then.
Correct.
Okay, I was kind of curious
Yeah.
why they were bigger.
Allison.
So you said initially that the ozone is influenced by the sun coming in, so the sun plays a role in this. Are there any plans to do this at a different time of year when you have different fluxes coming in?
I believe that DN is considering doing a long-term study at Adams Farm, so just sort of leaving Artemis there to see whether or not we can see like temporal variations.
So there would be an effect then?
We would most likely see that, yeah. I mean, based on temperatures, the production would probably be decreased and reactivity in the air would probably also be lower.
So I guess it was
So
conveniently that you guys went out in the summer, but it was actually probably like it would enhance your data as well to go out in the summer.
Yes and no.
Think about mixing. So in the winter you get stratification and it can get trapped in a thinner layer of the atmosphere.
Cool.
And so in the winter you can get even higher levels, but it's because what you're making isn't mixing as much.